Okay, so we're up to module 13 of ENSA, which is network virtualization. Right, so we're going to talk about cloud computing, virtualization, virtual network infrastructure, software-defined networking, and controllers. So cloud computing. Cloud computing addresses a variety of data management issues. It enables access to organisational data anywhere and any time, streamlines the organisation's IT operations by subscribing only to needed services, eliminates or reduces the need for on-site IT equipment maintenance and management, reduces cost for equipment, energy, physical plant requirements and personal training needs, enables rapid responses to increasing data volume requirements. So the three main cloud computing services defined by National Institute of Standards and Technology in their special publication 800-145 are as follows. So software as a service, which is the cloud provider is responsible for access to application services that are delivered over the internet. Platform as a service, so the cloud provider is responsible for providing users access to development tools and services used to deliver the applications. And then infrastructure as a service, the cloud provider is responsible for giving IT managers access to the network equipment, virtualized network services, and supporting network infrastructure. Cloud service providers have extended this model to also provide IT support for each of the cloud computing services. ITaaS. For businesses, ITaaS can extend the capability of a network without requiring investment in new infrastructure, training new personnel, or licensing new software. Okay. So the four primary cloud models are public clouds, which of course are provided by large service providers. And so, Office 365 is probably the most common one people think of there. Private clouds, where the organisation itself creates its own cloud. It's only for use by that organisation. And so hybrid clouds are a cross between the two. So basically it's part private, part public. So if you need the stuff that public cloud supplies, why not use it? And then for any special needs that you might have, of course, you can use a private cloud for that. And so they're connected together to create a single architecture. And then community clouds are created for exclusive use by a specific community. The differences between public clouds and community clouds are the functional needs that have been customised for the community. For example, healthcare organisations must remain compliant with policies and laws, e.g. HIPAA, that require special authentication and confidentiality. Okay, so cloud computing versus data centre. There are correct definitions of data center and cloud computing. So data center is typically a data storage and processing facility run by an in-house IT department or leased office offsite. Data centers are typically very expensive to build and maintain, while cloud computing, typically an off-premises service that offers on-demand access to a shared pool of configurable computing resources. These resources can be rapidly provisioned and released with minimal management effort. Data centers are the physical facilities that provide the compute, network and storage needs of cloud computing services. Cloud service providers use data centers to host their cloud services and cloud-based resources. All right, virtualization. So the terms cloud computing and virtualization are often used interchangeably. However, they mean very different things. Virtualization is the foundation of cloud computing. Without it, cloud computing, as it is most widely implemented, would not be possible. But virtualization separates the operating system from the hardware. Various providers offer virtual cloud services that can be dynamically provisioned servers as required. These virtualized instances of servers are created on demand. And so that's AWS, Amazon Web Services, as a management console. Okay, so historically enterprise servers consisted of a server OS such as Windows Server or Linux Server installed on specific hardware. All of the server's RAM, processing power and hard drive space were dedicated to the service provided, be that webmail, email, whatever it might be. When a component fails, the service that is provided by this server becomes unavailable. This is known as a single point of failure. Dedicated servers were generally underused. They often sat idle for long periods of time, waiting until there was a need to deliver the specific service they provide. These servers wasted energy and took up more space than was warranted by the amount of service provided. This is known as server sprawl. So with server virtualization, it takes advantage of idle resources and consolidates a number of required servers. This also allows for multiple operating systems to exist on a single hardware platform. The use of virtualization normally includes redundancy to protect from single points of failure. The hypervisor is a program, firmware or hardware that adds an abstraction layer on the top of the physical hardware. The abstraction layer is used to create virtual machines which have access to all the hardware of the physical machines, such as CPUs, memory, disk controllers, and NICs, etc. And so here we can see we've got two servers and they've got multiple instances of the operating system running on the same piece of hardware. So we've got 4 instances of Windows running, all doing a different job. And so on this one, it's doing much the same job. And so it's the hypervisor that's between the operating system and the hardware. Normally, it's the operating system interacting directly with the hardware. Okay, so what are the advantages? One major advantage of virtualization is overall reduced cost. Less equipment is required, less energy is consumed, less space is required. There are additional benefits as well, so easier prototyping. Well, we need a new server. You don't have to buy a specialized box for that now. You can just create a new instance of a VM as long as you've got enough resources. Faster server provisioning, increased server uptime, improved disaster recovery, and you can support legacy operating systems in the virtualization. Abstraction layers. So a computer system consists of following abstraction layers. So services, operating system, firmware, and hardware. At each of these layers of abstraction, some type of programming code is used as an interface between the layer below and the layer above. A hypervisor is installed between the firmware and the OS, and the hypervisor can support multiple instances of operating systems. So this left one is the traditional setup, and the right one is with a hypervisor in the middle. So that's how you get your multiple operating systems running. Type 2 hypervisors. So they are a software that creates and runs VM instances. The computer on which a hypervisor is supporting one or more VMs is a host machine. Type 2 hypervisors are also called hosted hypervisors. The big advantage of Type 2 hypervisors is that management console software is not required. So basically, if I were running virtualization on my computer here, the Windows operating system I'm operating is here, then you install VMware Workstation or Hyper-V or, oh God, I've forgotten the other one. Anyway, and so from there, of course, you can have multiple other instances. So you've got the host operating system and the 3 guest operating systems, basically. Okay, virtual network infrastructure. So Type 1 hypervisors are also called bare metal approach because the hypervisor is installed directly on the hardware. Type 1 hypervisors are usually used on enterprise servers and data center networking devices. With Type 1 hypervisors, the hypervisor installed directly on the server or networking hardware. Then instances of an OS are installed on the hypervisor as shown in the figure. Type 1 hypervisors have direct access to the hardware resources, therefore they are more efficient than hosted architectures. Type 1 hypervisors improve scalability, performance and robustness. So yeah, that's normally what your server will be using. So be that Hyper-V, if you're running a Windows Server OS, that would be what you could do. And of course there's vSphere and all kinds of other solutions from other vendors. So how do you install a VM on a hypervisor? Type 1 hypervisor require a management console to manage the hypervisor. That software is used to manage multiple servers using the same hypervisor. It can automatically consolidate servers and power on or off servers as required. The management console provides recovery from hardware failure. If a server component fails, the management console automatically moves the VM to another server. Cisco Unified Computing System, or UCS manager, controls multiple servers and manages resources for thousands of VMs. Some management consoles also allow servers over allocation. Over allocation is when multiple OS instances are installed, but their memory allocation exceeds the total amount of memory that the server has. Overallocation is common practice because all 4 OS instances rarely require all of their allocated resources at any one moment. Okay, so the complexity of network virtualization. So server virtualization hides server resources. This can create problems when using traditional network architectures. VMs are movable and network administrator must be able to add, drop and change network resources and profiles to support their mobility. This process would be manual and time consuming with traditional network switches. Traffic flows differ from traditional client-server model. Typically, there is a considerable amount of traffic being exchanged between virtual servers, so east-west traffic as opposed to north-south, that changes in location and intensity over time. North-south traffic is typically traffic destined for off-site locations such as another data center or other cloud providers or the internet. So dynamic, ever-changing traffic requires a flexible approach to network resource management. Existing network infrastructures can respond to changing requirements related to the management of traffic flows by using quality of service and security level configurations for individual flows. However, on large enterprises using multi-vendor equipment, each time a new VM is enabled, the necessary reconfiguration can be very time consuming. Network infrastructure can also benefit from virtualization. Network functions can be virtualized. Each network device can be segmented into multiple virtual devices that operate as independent devices. Examples include sub-interfaces, virtual interfaces, VLANs, and routing tables. Virtualized routing is called virtual routing and forwarding, or VRF. All right, software-defined networking. A network device contains the following planes, so a control plane and a data plane. And so the control plane is typically regarded as the brains of a device. It is used to make forwarding decisions. The control plane contains layer 2 and layer 3 route forwarding mechanisms such as routing protocol neighbor tables and topology tables, IPv4 and IPv6 routing tables, spanning tree and ARP tables. Information sent to the control plane is processed by the CPU. Then the data plane, or the forwarding plane, typically the switch fabric connecting the various network ports on a device. The data plane of each device is used to forward traffic flows. Routers and switches use information from the control plane to forward incoming traffic out the appropriate egress interface. Information in the data plane is typically processed by a special data plane processor without the CPU getting involved. All right, so control plane and data plane. So Ceph is an advanced layer 3 IP switching technology that enables forwarding of packets to occur at the data plane without consulting the control plane. SDN is basically the separation of the control plane and the data plane. The control plane function is removed from each device and is performed by a centralized controller. The centralized controller communicates control plane functions to each device. Each device can now focus on forwarding data while the centralized controller manages data flow, increases security and provides other services. And so we did talk about Ceph in a previous chapter. And so basically just taken Ceph to its most extreme version, I suppose. All right, so the management plane is responsible for managing a device through its connection to the network. Network administrators use applications such as SSH or TFTP, Secure FTP, Secure Hypertext Transfer Protocol to access the management plane and configure a device. The management plane is how you have accessed and configured devices in your networking studies. In addition, protocols like Simple Network Management Protocol use the management plane as well. So, two major architectures have been developed to support network virtualization. There's software-defined networking and there's Cisco application-centric infrastructure, or ACI. So SDN is a network architecture that virtualizes the network, offering a new approach to network administration and management that seeks to simplify and streamline the administration process. While ACI is a purpose-built hardware solution for integrating cloud computing and data center management. Okay, so components of SDN may include the following. So OpenFlow, OpenStack, and other components. So OpenFlow, this approach was developed by Stanford University to manage traffic between routers, switches, and wireless access points, and a controller. The OpenFlow protocol is a basic element in building SDN solutions. So OpenStack is a virtualization and orchestration platform designed to build scalable cloud environments and provide an IaaS solution. OpenStack is often used with Cisco ACI. Orchestration is networking in the process of automating the provisioning of network components such as servers, storage switches, routers, and applications. Other components can be an interface to the routing system, transparent interconnection of lots of links, Cisco Fabric Path, and 802.1AQ, which is your shortest path bridging. Okay, so traditional and SDN architectures. In a traditional router and switch architecture, the control plane and data plane functions occur in the same device. Routing decisions and packet forwarding are the responsibility of the device operating system. In SDN, management of the control plane is moved to a centralized SDN controller. The figure compares the traditional SDN architectures. So, the SDN controller is a logical entity that enables network administrators to manage and dictate how the data plane of switches and routers should handle network traffic. It orchestrates, mediates, and facilitates communication between applications and network elements. The complete SDN framework is shown in the figure. Note that the application programming interface, or API, is a standardized definition of the proper way for an application to request services from another application. The SDN controller uses northbound APIs to communicate with the upstream applications, helping network administrators shape traffic and deploy services. The SDN controller uses southbound APIs to define the behavior of the data planes on downstream switches and routers. OpenFlow is a widely implemented southbound API. Okay, controllers. An SDN controller defines the data flows between the centralized control plane and the data planes on individual routers and switches. Each flow travelling through the network must first get permission from the SDN controller, which verifies that the communication is permissible according to the network policy. All complex functions are performed by the controller. The controller populates flow tables and switches manage the flow tables. Within each switch, a series of tables implemented in hardware or firmware are used to manage the flows of packets through the switch. To the switch, a flow is a sequence of packets that matches a specific entry in a flow table. The three table types shown in the previous figure are as follows. A flow table. This table matches incoming packets to a particular flow and specifies the functions that are performed on the packets. There may be multiple flow tables that operate in a pipeline fashion. Then you have a group table, which is a flow table may direct a flow to a group table, which may trigger a variety of actions that affect one or more flows. And then there's a meter table. This table triggers a variety of performance-related actions on a flow, including the ability to rate limit the traffic. Okay, there are three common core components of the ACI architecture. So there's application network profile, which is a collection of endpoint groups, their connections and policies that define those connections. There's APIC, or Application Policy Infrastructure Controller. It's a centralized software controller that manages and operates a scalable ACI cluster fabric. It is designed for programmability and centralized management. It translates application policies into network programming. And then there's Cisco Nexus 9000 series switches. These switches provide an application-aware switching fabric and work with APIC to manage the virtual and physical network infrastructure. And so the APIC is positioned between the APN and the ACI-enabled network infrastructure. The APIC translates the application requirements into a network configuration to meet those needs. Okay, so here's a bit of a diagram. So you got customers, VLANs, and so on. Got the APIC between it and the network. All right. Did I do more than one? No. So spine leaf topology. The Cisco ACI fabric is composed of the APIC and the Cisco Nexus 9000 series switches using two-tier spine leaf topology. As shown in the figure, the leaf switches are attached to the spines, but they are never attached to each other. Similarly, the spine switches only attach the leaf and core switches, not shown. In this two-tier topology, everything is one hop from everything else. When compared to SDN, a APIC controller does not manipulate the data path directly. Instead, it centralizes the policy definition and programs the leaf switches to forward traffic based on defined policies. Okay, so SDN types. So Cisco Application Policy Infrastructure Controller, or Enterprise Module, so APIC-EM, extends ACI aimed at enterprise and campus deployments. To better understand APIC-EM, it is helpful to take a broader look at the three types of SDN. So device-based is where the devices are programmable by applications running on the device itself or on a server in the network as shown in the figure, also using OpenFlow. Controller-based, where it uses a centralized controller that has knowledge of all the devices in the network as shown in the figure. The applications can interface with the controller responsible for managing devices and manipulating traffic flows throughout the network. The Cisco Open SDN controller is commercial distribution of Open Daylight. And then there's policy-based SDN, similar to controller-based, where a centralized controller has a view of all devices on the network as shown in the figure. Policy-based SDN includes an additional policy layer that operates at a high level of abstraction. It uses built-in applications that automate advanced configuration tasks via a guided workflow and user-friendly GUI. No programming skills are required, and so the APIC-EM is an example of this type of SDN. And so the APIC-EM provides a single interface for network management, including discovering and accessing device and host inventories, viewing the topology as shown in the figure, tracing a path between endpoints, and setting policies. The APIC-EM path trace tool allows the administrator to easily visualize traffic flows and discover any conflicting duplicate or shadowed ACL entries. This tool examines specific ACLs on the path between the two end nodes, displaying any potential issues. You can see where any ACLs along the path either permitted or denied your traffic, as shown in the figure. Notice how branch 2 router is permitting all traffic. Network administrator can now make adjustments if necessary to better filter traffic. I can hardly see branch router 2, but anyway. All right, that's the end of the module, so we'll just have a bit of a recap. So cloud computing involves large numbers of computers connected through a network that can be physically located anywhere. Cloud computing can reduce operational costs by using resources more efficiently. Three main cloud computing services defined by the NIST are software as a service, platform as a service, and infrastructure as a service. Four types of clouds are public, private, hybrid, and community. Virtualization is the foundation of cloud computing, and not the same thing. Virtualization separates the operating system from the hardware, puts a layer in between, the hypervisor. Virtualization reduces costs because less equipment is required, less energy is consumed, and less space is required. It provides for easier prototyping, faster server provisioning, increased server uptime, improved disaster recovery, and legacy support. With Type 1 hypervisors, the hypervisor is installed directly on the server or networking hardware. A Type 2 hypervisor is software that creates and runs VM instances. It can be installed on top of an OS or can be installed between the firmware and the OS. Type 1 hypervisors are also called bare metal approach because the hypervisor is installed directly on the hardware and they have direct access to the hardware resources and are more efficient than hosted architectures. They improve scalability, performance, and robustness. Type 1 hypervisors require a management console to manage the hypervisor. Server virtualization hides server resources such as the number and identity of physical servers, processors, and OSs from server users. This practice can create problems if the data center is using traditional network architectures. Traffic flows in the data center differ substantially from traditional client-server model. Typically, a data center has a considerable amount of traffic exchange between virtual servers, east-west, and can change in location and intensity over time. North-south traffic occurs between the distribution and core layers and is typically traffic destined for off-site locations such as another data center or other cloud providers or the internet. Two major network architectures that have been developed to support network virtualization are software-defined networking and Cisco application-centric infrastructure. Components of SDN include OpenFlow, OpenStack, and other components. A network device contains a control plane and a data plane. The control plane is regarded as the brains of the device. SDN is basically the separation of the control plane and data plane. Control plane function is removed from each device and is performed by a centralized controller. That controller is a logical entity that enables network administrators to manage and dictate how the data plane of switches and routers should handle network traffic. Data plane, also called the forwarding plane, is typically the switch fabric connecting the various network ports on a device and is used to forward traffic flows. The management plane is responsible for managing a device through its connection to the network. The SDN controller is a logical entity that enables network administrators to manage and dictate how the data plane of switches and routers should handle network traffic. Okay, the Cisco developed ACI, or application-centric infrastructure, which is more advanced and innovative than early SDN approaches. It's a hardware solution for integrating cloud computing and data center management. At a high level, the policy element of the network is removed from the data plane. This simplifies the way the data center networks are created. Three core components of ACI are application network profile, application policy infrastructure controller, and the Cisco Nexus 9000 series switches. The Cisco ACI fabric is composed of the APIC and the Cisco Nexus 9000 series switches using two-tier spine leaf topology. When compared to SDN, the APIC controller does not manipulate the data path directly. Instead, the APIC centralizes the policy definition and programs the leaf switches to forward traffic based on the defined policies. There are three types of SDN, so device-based, controller-based, and policy-based. Policy-based SDN includes an additional policy layer that operates at a high level of abstraction. Policy-based SDN is the most robust, providing for simple mechanism to control, manage policies across the network. APIC-EM is an example of a policy-based SDN. It provides a single interface for network management, including discovering and accessing devices and host inventories, viewing topology, tracing a path between endpoints, and setting policies. It has a trace tool that allows the administrator to easily visualize traffic flows and discover any conflicting, duplicate, or shadowed ACL entries. This tool examines specific ACLs on the path between two end nodes, displaying any potential issues. There is the logo. One more chapter to go after this. We've got chapter 14 and the way we roll. Have a good one.